Hello out there. It's that time. Time to get our science on and hopefully not listen to my two dogs. Hopefully they'll get along tonight. If you hear me, could you please type a little something in the little chat? That way I know that you're here and that you can hear me and my microphone's working perfectly fine. If you can do that, I greatly appreciate it, please. Because it's time to rock and roll. Alrighty. Excellent. Thank you, Carla. I appreciate it. All right. I just got a message on my watch that I'm starting my stream right now. Sweet. All right. So without further ado, let's get into what we're talking about tonight. So this is a portion of, actually, it's the current unit that I'm working on right now. So we're talking about Earth's atmosphere, all the Earth stuff. There was a stream a couple days ago, and then we have tonight's stream here is all about Earth's atmosphere and global wind. So basically, how things get around on the planet in the air. Okay. So I do appreciate all you guys coming tonight, taking time out of your busy schedules. I know I'm getting ready for next week will be my last week, and then I get to go to Thanksgiving break. So hopefully you guys will have some fun the week after next. All right. So again, my name is Mr. Nielsen, Joshua Nielsen. I've been an H teacher for 7 years now. And I will tell you right now, Earth stuff, this is my least favorite unit, except I do like talking about soils. I like to get my hands dirty and play with the soils. We actually did the soil lab today in my class. And I kind of like talking about the atmosphere. Now, all the rest of it, I can take it or leave it, but I do like talking about these materials specifically. So hopefully we'll have a little bit of fun. Now, before we actually do begin, let's make sure that I talk about this. We, of course, at Fiveable are on all of our lovely little digital items. We are at the Twitter, the YouTube, and of course the Instagram at Think Fiveable. Okay, so please give us a like out there. Tell your friends. Hopefully, they'll get something out of it just as much as you are getting something out of it. So here is my goal for tonight. Only two simple ones. Unfortunately, they are rather numerous pieces of it. So if you have questions, comments, concerns, please type them in the chat. I will get to them as soon as I possibly can. I want to be able to answer as many questions as I can. If I can't answer the question, hopefully I'll be able to point you in the right direction so that you can get the right info. Okay. Now, in a couple of places, I will be doing that tonight. So like I said, what we're going to be doing tonight is looking at Unit 4.4, the Earth's atmosphere, all its components, and 4.5, the global wind patterns. All right. And my dog wants to annoy me right now. She needs to stop. Okay, so Earth's atmosphere 4.4. Let's get into it. Before I actually give you some information, I need you to give me a little bit of information. Please answer this question if you can. What would happen if the Earth's atmosphere were to just totally disappear tomorrow? Take a moment. Think about it. Right in the comment section. What do you think is going to happen if all of a sudden, bam, Earth's atmosphere is gone entirely? Similar to what you see in Spaceballs when, yes, we'll boil, actually. A lot more radiation. Plenty of death. Plenty of it. If you guys have ever seen the classic movie Spaceballs, this is when Mega Meg sucks all the air out of the planet. So you can see, we're not going to see trees uplifting or anything like that. But, yeah, there is going to be a lot of death. Oh, it is. Yeah, it's a great movie. Absolutely great. Lots of great movies around that time. So here, all your answers are absolutely perfect, spot on. There's a few more I'm going to talk about right here. If you hear my dogs in the background, I do apologize. They love each other so much. So life without the atmosphere. There will be something about the ozone layer. The ozone layer itself is part of the atmosphere. So that's actually going to take care of our radiation right there. No more breathing. There's going to be no more photosynthesis because all the carbon dioxide's gone. And we can't breathe because all the oxygen is gone. And it's not just the oxygen we take in our body, we take in the rest of it too, but it's the oxygen that we're going to use the majority of. Skin cancer. So Carla said there's going to be more radiation. Yeah, that skin cancer is going to be more prevalent if we're able to survive. If not, then you're going to see a lot of genetic damage because of that solar radiation right there. Even if you notice the gentleman in the bottom left of your screen, he's got the little air tank gas mask. Even he would not be able to survive because of the lack of air pressure. He would actually explode. We will see extreme differences in day and night, and even then, basically we wouldn't even have seasons. We'd have hot, we'd have cold. We're going to be very similar to what we see on Mercury, which has no atmosphere. It has an atmosphere, but it's constantly blown away. So Mercury has no atmosphere almost. The image you have on your screen, that's not Earth. That's actually Mars. I was trying to find a good image of Earth without any air or any water, but it just wouldn't happen. So Mars has next to no atmosphere as well. And you can see it became very dry, very lifeless. And if you follow the Martian rovers, like I used to do a lot of, the temperature differences between day and night are insane. It's worse than what you would see in the deserts. Much more than just a 50 or 60 degree turn. You're looking at a few hundred degrees Celsius differences between those because of the lack of atmosphere. It helps to regulate a lot of this temperature throughout the globe. And of course, hopefully you guys remember way back when we talked about the have you guys discussed biogeochemical cycles? It should have been one of the earlier units. I'm hoping that you have. I'm not asking you to remember about it, but almost all of those biogeochemical cycles have a component that go into our atmosphere. There's only one that doesn't touch the atmosphere. Do you guys remember which one it is? Remember which of the major biogeochemical cycles does not have a atmospheric component? It's okay if you don't. That's right, phosphorus cycle. Thank you, Dakota. Yes, Scarlett, yes. It is phosphorus. It's going to be only broken down in the rocks, and it'll get into the soil and then run off into your waterways too. It's the only one that is not going to be affected because of the lack of atmosphere. But a lot of the breakdown of the rocks from phosphorus is going to be from rain. And if we don't have atmosphere, we're not going to have rain. So even that will be affected by our lack of air around us. And because of the lack of air, again, now we have no pressure holding our oceans together. The lack of pressure is going to basically take care of the boiling point of our oceans, and they will instantly boil away, just like your blood would actually boil from the lack of pressure. Physics is a funny thing. I'm definitely not a physics person. I'm a biology guy, but I can tell you right now, the boiling ocean and all that, not only all the fish are dead, but all the algae that helps to make our oxygen, everything is gone. All because there's no more atmosphere. So a lot of people take our atmosphere for granted, the air that we're breathing. It is life-sustaining in more than just the ability to bring in oxygen. It's just amazing. Okay, so I do like this section. Okay, so any questions or comments or concerns? Anything I can help you out with so far? Well, actually, so one of the things we'd like to do is go to Mars, but because the lack of oxygen, although we're finding evidence that there's possibly a little bit there and some methane, it has a very thin atmosphere. So again, there's a little bit there, but we'll still have to use these spacesuits and all that to add pressure to our body so that our blood doesn't boil and such. They are developing lovely little, kind of like the little drones that you can purchase, but they had to specifically design a drone that can be able to fly in very low atmosphere. So what they'll do is they'll put it into a really large vacuum chamber and basically give the approximate amount of atmosphere that you would see on Mars. and test all their little drones to see if they can fly. And they're supposed to be sending them over the next time they launch a mission to Mars. I absolutely love space travel. That kind of thing just gets me going. I love that kind of stuff. Alrighty. So let's continue with what is the atmosphere made up of? Now, obviously, I can't answer your question, what do you think it's made of? Because I put the pie charts on the side. Kind of silly of me. I should have hidden those. But a lot of people outside of the class are really, really surprised that the majority of the air that you breathe is nitrogen. We think of air as a big soup, okay? And like a lot of things in soup, I don't like all the parts of my soup. I only like the noodles and like the chicken part of it. The broth I was never big on as a kid. And so the majority of our broth is going to be that nitrogen, which is about 78% of all the air that we're breathing in. Funny thing is, we don't use any of that nitrogen. It's strictly for the plants and the other producers. When we eat them, then we can get our nitrogen. But from the air itself, does not affect us. It just helps to add to the soupiness of our air. The next component, obviously, as you can see right there, is oxygen. About 21%. It's actually 20.96, I think it is. When you breathe that in, helps you allow you to do cellular respiration. Sorry for the squeaky dog toy in the background. You won't even use all that oxygen. You'll actually breathe a portion of it back out. That way you can breathe in and out of that paper bag and not pass out immediately because you're only using a portion of the oxygen. You'll breathe it back out. Those are the two largest ones. The next one, again, the next largest one is argon, which is one of those lovely noble gases that doesn't like to play well with others. And from there, a whole bunch of trace gases, and of which, carbon dioxide happens to be one of them. Now, we are really worried about this carbon dioxide stuff. And it's because you'll notice on this middle chart, it's been rising quite some time now. A lot of people will not argue the fact that it's rising. What do they usually argue about when it comes to carbon dioxide in their atmosphere? You don't see the chart? It's not in the middle of the screen? Should be the little wavy red and blue line. Oh, okay. Whew. I got scared for a second there. I was like, I can see it. So you can, like I said, you can see that, and it's not a really large graphic right there. No, actually, the carbon dioxide is not what's depleting the ozone layer. When you guys get to the pollution section, I would have talked about it tonight, but it's part of the pollution section, really. It's not ozone that does that. It's mostly chlorofluorocarbon. So there is a little bit of carbon in it, but it's not the actual carbon dioxide. So a lot of people will not argue the fact that, you can see we are rising in the amount of carbon dioxide in the atmosphere. It's playing tricks on you. I have not seen it move on my screen. Is it like blinking in and out on your screen? That is so weird. Yeah, go ahead. Yeah. Refresh your page and see. Okay, well, let me just describe it. So, for the past at least 60 to 70 years, we can see that we have a huge spike in increase in carbon dioxide. You go back at least 150 years, you can see that's when it started to increase. And it's kind of steady, and then it starts to go up rather rapidly, almost exponentially. And again, they're not going to argue that it's happening. It's why it's happening. So a lot of people will poo-poo the fact that it's anthropogenic carbon dioxide in the atmosphere. So we are releasing it. There has been patterns where there's been an increase and decrease in over the millennia with carbon dioxide, and it will constantly go up and down. But we're noticing that there's a huge acceleration of that amount of carbon dioxide in the atmosphere. And so this number that I happen to have on the screen was that was the reading from 2018, so just a year ago, and it is 0.04% of our atmosphere, or basically 4 parts per, is it 4 parts per million or billion? I'm trying to remember. And that's the highest it's ever been since humans have recorded it with humans on the planet. So we're really concerned about that because of its uh, greenhouse gas effects, that thermal blanket. All right. So the other one here is methane, which for greenhouse gases, it's between 5 and 10 times as worse, more potent or more deadly than carbon dioxide. But you can see that's insanely smaller compared to the amount of carbon dioxide. And then again, a few more things that I didn't even put on this list. What I didn't mention earlier is the amount of water in the atmosphere. Depending on where you're located, it can be anywhere between 0 and 4%. Again, I say locally because if you look at the ocean, you're going to have a lot more water in the atmosphere. But if you look at Dead Valley, there's none whatsoever. And so the other numbers, mostly the nitrogen and oxygen, will fluctuate because of the amount of water in the atmosphere. And water itself does change what happens to the areas around you right there. Okay. Cool thing is, you really don't have to have all of these memorized. You just have to really worry about nitrogen is the largest component, which humans are not really able to use except for through plants. Oxygen is the second largest, about 21%. Carbon dioxide as a trace gas is basically your thermal blanket, your greenhouse gas. Water is also a greenhouse gas too. Carbon dioxide is just really, really good about it too. All right. So, Sarah, I hope you can see some graphs on here because these ones are rather important. This is talking about air pressure. The way I think about air pressure, of course, is basically this huge column of air. Here, I'm going to use my little water bottle here. So if I'm standing right here where my hand is, all the air above it is pushing down on me. Okay. That is what we call air pressure. It's very similar to what you experience if you go to the bottom of the pool. You tell me, what do you feel when you go to the bottom of the deep end of a pool? Because the kiddie pool is not going to help, but you have to go to that 10, 12-foot section. What do you experience down there? There's a lot of pressure. Now, is it pressure pushing in or pressure of your head pushing out? So if this was one of those FRQ questions, you'd have to specify. You can't just say one or the other. I mean, you can't just say it's pressure. You have to specify. They're really looking for those things. Yeah, so you have all that pressure pushing in. Okay. I always tell my students, pretend that the reader, the person who's grading your FRQs, is a complete moron and kind of explain it out a little bit. I have been a reader for, 4 years now? Yeah, I think it's like that, 4 years. And so, yeah, we're looking for those little things. We're told we can't just give those points unless they specify. So just saying pressure wouldn't help. You have to say, yeah, all that pressure is pushing because all that water is crushing down on your head. So the same thing happens with air. We don't necessarily feel it because we're used to it. We were born with this constant pressure on us, so we're very acclimatized to it. Okay. At sea level, we consider it to be 1 atmosphere. Okay. So if you were to make that measurement, we consider that to be 1 atmosphere. As you go higher up, there's less air above you. So you'd have, it'd be less than an atmosphere. If you were to put these into other terms, 14.7 psi, which is pounds per square inch. You'll notice that's the same that you put on when you're filling up the air in your tires. 760 milligrams of mercury or 1013 millibars. None of those numbers you technically ever have to worry about. You just have to know that this is what we consider to be the units of air pressure itself. More than likely, if you ever have to play with those numbers, they're going to give them to you as one of the standards because that's exactly what they are. So I just want to make sure that you're familiar with those terms. So again, as altitude increases, the pressure will decrease, and I'm hoping, Sarah, you see this. That's what that top graph is showing. Thank you, dogs. That the higher up you go, there's less and less air above you, so therefore you have less and less pressure pushing down on you. So when they put the weather balloons, they will not fill them all the way up with air because as the balloons go up higher and higher, there's less pressure pushing in on them, and they'll start to expand. until they pop if they're not if they're too full of air originally. All right, let's continue. So we consider this to be again an inverse relationship. Okay, now can atmospheric pressure create weather conditions? Hopefully, you've seen this on the weather maps. Yeah. So when they're talking about highs and lows, I really did not totally understand this until because I'll tell you right now, I'm quite sure I was taught this when I was in junior high. Did not really stick until I started teaching the class. Those high pressures, you have a lot of air pushing down on you. So you look at the little H's that I have, the little H and L with the arrows. If you have a lot of high pressure, it's going to push down on there and it's going to basically push down and push away all those clouds. So normally we think of like sunny skies. This is when you get to have nice clear skies, usually a little bit more higher temperatures because of that increased pressure. Oh, I clicked on the wrong button for me. Here we go. Low pressure, since there's less air or there's less pressure pushing down on it, it's can actually tend to go up. So as the air goes up, the air on the sides will come towards, and then basically we're kind of like a little convection current is happening right there. And when that happens, all this air rises up, and we'll talk about adiabatic cooling here in just a few minutes. It'll start to cool, and that's when you start to get rain clouds. So low pressure usually is rain, clouds, or at least lower temperatures too. Does that make sense? If you ever look at the Weatherland map, it's again talking about where high pressure and low pressures are coming in. Good, because like I said, didn't really stick in junior high. Didn't really stick in. Until I started just hearing. Can you still hear me there, Sarah? You may have to refresh. Let's see. I'll move my head around a little bit. Okay. It might be a connection issue on my side. I don't know. My son's not home to play video games, so should be lots of bandwidth right now at my house, but never can tell. All right, so here's one of my favorite things that I have to talk about with my students, and I usually use a little folded piece of papers with this. It's the layers of the atmosphere. Okay, how many of y'all? This is the first time that you've talked about layers of the atmosphere was in this class. Stratosphere, yeah. So troposphere happens to be where we live. Now, you may have to try to remember the layers. So people much wiser than I am came up with a beautiful little mnemonic. Oh, hold on now, Sarah. The lithosphere is not part of our atmosphere. That's actually a part of the layers of the Earth, too. All right, so part of our crust. Oh. All right, I'm beginning to wonder if that it's my computer that's freezing. I'm sorry, y'all. Hopefully, I will get this taken care of soon. All right, so here is the lovely little mnemonic that we have. Tiny soldiers make tents expertly. I like mnemonics. I like silly little mnemonics because they'll stick in my brain way better. I'm typing in there, are you hearing me? Okay. So tiny soldiers make tents expertly. If you look at this, tiny is the very bottom and you work your way up. Just can't see me. All right. Hold on. Let's see. Hopefully you see nothing but my face right now. I swapped screens. Do y'all see that? Stroking my beard, making it look like I have big, wise thoughts. It's a very long beard. I'm going for wizard level. And I hope it doesn't freeze later because I've got a really special website I really want to need to show y'all that's Absolutely brilliant. Okay. Can't see me. This is not fun on my part because I have no problems on my side that I can see, but it's apparently affecting you. I'm very upset by this. Carly says it's working fine for her. Okay. All right. Well, I'm going to continue, but of course, this will be up on the Fiveable website and all that. And hopefully, oh, thank you, Maya. Is it Maya or me? Like, that's silly of me to ask you a verbal question like that and you can't respond. All right. So, uh, easily you can see these if you do a quick little Google search, but I'm going to try to talk my way through it right here. Yeah, the slides is going to be it will be on the on Fiveable on there. It will be uploaded. I will have it up there actually, I'm taking the day off of school tomorrow, so it will be up there tomorrow once I get this video downloaded tonight. So you should be able to see it easily, and hopefully there will be no freezes or anything like that. If there is a problem, then hopefully you can contact me through Fiveable or whatever, and I'll see what I can do about sending you to nice little websites or links and all that. So let me continue on with this, and then hopefully we'll have few errors tonight. So let me start off with the troposphere. Troposphere is the very bottom. It's it is not one of the smallest. It is the absolute smallest layer. This is where life occurs. This itself, what we're doing, what we are, all of us. It's also where weather will occur. Okay, there will be a little bit of weather above us, but for the most part, this is where you get to have all your clouds and such. Almost all the clouds. There's a few of those high, wispy ones that are outside the troposphere. Even the troposphere again is taller than even the mountains. This is where you're going to see the majority of your airplanes flying. Okay, not big commercial jets. They can go even higher up. They get to go into the stratosphere. Now, I'll talk about the little lines that are on my diagram here in a few minutes. But stratosphere, this is where you get commercial airliners. Okay, if you look on the map, or if you can't, it's approximately 15 miles above or kilometers above the surface of our planet itself, above sea level. That's what we get into the stratosphere. Now, as you notice in the image, if not, then think about it. As you climb up a mountain, it'll get colder and colder. The top of Mount Everest is way colder than the bottom down there. So as we climb up in the troposphere of our atmosphere, it will begin to get colder. Okay. And part of it is because there's less pressure, less density. But once we hit the stratosphere, it will begin to become warmer a little bit. Up to, when I say warmer, up to like about just shy of 0 degrees Celsius. So it's still nothing you're going to be able to be happy about, but it will be warmer. So we're going to see we get colder. Again, if we have 0 over here and really warm over here, as we go up in the troposphere, it gets colder, and then it begins to level off at what we call the tropopause, and it'll become warmer in the stratosphere. Stratosphere, basically all we care about there is this is where we happen to have some commercial airplanes. And then there's this funny thing like weather balloons. Oh yeah, and the ozone layer, that life-sustaining, no radiation, going to give me skin cancer type thing. You're going to see the ozone layer here in the stratosphere. All right, this is one of the main things that you have to worry about. Troposphere is life. Stratosphere is ozone layer. You don't have to actually know like which portion of the stratosphere, but this is where your ozone layer is occurring. Okay, so when you get to the pollution section, that's when we'll start talking about how the ozone layer is created and or destroyed. Next, we get the mesosphere. Again, it gets insanely cold again, like really super cold, almost to a negative 100 Celsius. This is the world's most boring atmospheric layer. It's rather thick and nothing happens here. It's just cold and boring. There's nothing exciting here that happens. Oh, except for meteors burn up here. That's about it. Other than that, nothing else. It's just boring. So like when you see shooting stars, the Linead meteor shower that happened, what was it, a month ago, 2 months ago? This is where the majority of those chunks are burning up, and it's because there's just enough air particles to create friction to cause them to burn and get destroyed. Now, if they're big enough, then they can fall all the way through the mesosphere or the mesosphere and down, down to Earth itself. But this is where you're going to see that, that fireball happen, because there's just enough particles in the atmosphere to cause that friction to occur. You don't see the stratosphere heading and the rest of them. Oh, you're not seeing the stratosphere? Again, it's going to be, yeah, okay. I'm sorry, Sarah. Dang it. What I would suggest to do is do a quick just, and again, I don't know if it's on your end or my end, but if you'll just, if you can, log out, log back in, or just close your browser and open back up and come back in. I will attempt to talk a little bit slow, so that you're not going to miss much. But again, I can send you to some places to see this information. I can hopefully even send you to the exact locations I got some of the information from too. It wasn't all just from my textbook. Almost last but not least, we have our thermosphere, and we call it that because this is where it becomes very hot. Even the term thermo means insanely hot, and it will change rapidly with height. Okay, you get to see here the aurora borealis and the northern and the southern lights. I'm sorry, off the top of my head, I cannot remember the name for the southern lights. I'm originally from Canada, so I was constantly watching the aurora borealis. It was absolutely beautiful. And at certain times, because of solar radiation hitting our planet, you can see it even as far south as, the northern parts of the U.S. Absolutely. It's just beautiful. It's just breathtaking right there. And it happens right there in the thermosphere. And we consider that to be almost the outer edge of our atmosphere. There is one more layer of atmosphere, and we'll talk about that here. You're going to see all of our satellites, or a lot of our satellites. I won't say all of them, but the majority of our satellites are going to be in this thermosphere. The International Space Station is sitting there in the thermosphere itself as well. So technically, the International Space Station is not in space. It's more like the International Thermosphere Station, but that's just not nearly as catchy. Besides, that spells ITS instead of ISS. So NASA likes their acronyms to be a lot catchier than that. The last one is the exosphere. Exo meaning, of course, that's the prefix for outside or exterior. This right here, this exosphere, can actually reach all the way out about halfway between us and the moon itself. Is considered the limits of the exosphere. Even though there's like next to no particles of what we call air, it's still part of what we consider to be our atmosphere. A lot of people will combine thermosphere and exosphere and a portion of the mesosphere into what we call the ionosphere, where you have ions of our atmosphere sitting in there. So oxygen, the nitrogen, and a few of them here and there. Okay. So if you ever see ionosphere, it's a combination of mesothermo or thermo-exo. Most people are not going to discuss that part, so don't worry about that. Now, the last part I want to mention is there's what we call a pause in between the major layers. So between troposphere and stratosphere, we have the tropopause. Between stratosphere and mesosphere, we have the stratopause. And then we have the mesopause between the mesosphere or mesosphere and thermosphere. And those pause locations, they're various thicknesses, but you're going to see characteristics of both. On the image I have on the screen, that troposphere, at the very top of it, right where it touches the tropopause, this is where you'll have a different density of air, and that's when you get those flat top clouds. It's really neat. I never knew of it. I never knew as a kid as to why you'd have those flat tops, but it's where it hits that tropopause, and there's a mixing of the air characteristics there. And again, it just makes those flat top anvil shapes. It's to me that was just amazing. When I was a kid, I was always fascinated by that kind of stuff. All right, so I know I'm doing a lot of talking. I haven't asked a lot of questions. I do apologize. So let me go back. I'm sorry. Do you have any more questions I can help answer about these layers of the atmosphere and some of their characteristics? If you have no questions, we can go. Oh, it's not clause, it's the pause, and with a P. And basically, it's called that because there's it's not changing as much. The temperature will decrease as you go up the thermal as you go up the troposphere. Then there's a pause in the temperature change. It will just stay very, very steady. And then once you fully get into the stratosphere, it'll start changing again. They're defined not only by temperature. We'll see temperature differences, but they're actually defined by heights, their distances above sea level. And again, it's kind of a wishy-washy. It's not exactly from here to here. We just happen to notice that the temperatures will change due to where we're looking at inside the atmosphere itself. So, again, layers are not defined by their temperature. The temperature just happens to be a characteristic of the layers. The layers themselves are more defined by height and distance from the sea level itself. All right, so are we good? Can we continue on to global weather patterns? Or do you have more questions? All right. Sarah says yes. We got a second yes. We hear a second? All right, there's a second. Let's talk about global wind patterns. So I'm really excited about this one because I've got this beautiful website. Hopefully you've never seen it, so I can wow you tonight. But if you have seen it, then you already know how special it is. So we'll get to that here in just a few minutes. But once again, I have a question for you. What determines air circulation patterns? What determines where the wind goes? Excellent, Sarah. It is the ocean. That is a portion of it, but it's not all of it. A lot of it is from the ocean, but not all of it. There are some other characteristics. Now, I can tell you right now, I happen to live in Texas, and it was rather cold a couple of days ago, and it wasn't because of the ocean doing that. That's right. That's the other part is Earth's rotation. There's a few more things in here. Some of it actually we already talked about. So far so good. Earth's rotation is a big one, and I happen to have a beautiful globe right here, so we can talk about how the Earth's rotation will affect wind. I specifically remembered to bring it home from school today, so I can draw on it. All right. So, wind currents. Okay, global wind patterns. So here's a few things. Some of them you guys already mentioned. Oh, yes, heat. Don't forget heat. Thank you, Carl. I forgot. I didn't see that earlier. I apologize. So factors that will determine air circulation. All right, so air density. Okay, if it's very thin air, you can feel it moving, but not nearly as much as thick air. So think of like you can feel fog hit you, but not, just a little breath of wind. So air density, again, that's that high and the low pressure we talked about earlier, how they're going to go. It's just like in most things inside the cell, you always go from high to low pressure. You go from high concentration to low concentration. So we have that flow right there. Okay. Also, you'll notice even on this image right here, warm air will rise, hot air balloons, right? We don't have cold air balloons. We have hot air balloons because that's what's going to cause them to rise up. Cold air will sink. All right. The amount of water vapor, too, can determine how your wind blows and where it blows. All right. And for the most part, we're not only snooty and call it water vapor capacity. Just call it humidity. But humidity can determine where your wind is going to go, where it blows. All right, so here's some fun words. How many of y'all have ever heard of adiabatic heating and adiabatic cooling? You don't have to know what it means, but how many of you have heard about it? Yeah, so it took me a while just to be able to learn to pronounce the words adiabatic. Okay, here, I'll type it in there so that if you can't see the screen, it's, like I said, it's kind of weird. Adiabatic, heating and cooling. So hopefully I'll be able to teach you something cool and new today. Is adiabatic heating and cooling. Basically, this is based on pressure. Okay, well, let me go back a little bit. Let me double check. Yeah. So what we have right here, let me slow down. Let me talk about adiabatic heating and cooling. I don't remember if on my next slide or not, but let me talk about it here. So we see on the image, we have this lovely little ocean and wind is blowing on the ocean. So it's going to pick up some water. And as the water goes up the mountain, it will begin to condense. So this is what we call, this heating and cooling right here. As it goes higher, again, the warm air will go up. But again, as we go up higher in the atmosphere, it starts to get cooler. So there's less pressure. It'll start to expand and gets cooler. So the water droplets will condense. And that's how we're going to get these clouds. That's adiabatic cooling. The heat from that, from the ocean or, the land itself is going up. It'll start to expand. So now we're getting these big, massive clouds. And the water will begin to cool. So now we're going to get little rain droplets, and then it'll start to rain. And we're going to see that on this side of the mountain. Now, the opposite is happening as we go over the other side of the mountain. As the air sinks, it'll start to warm up because we're getting warmer and warmer as we get lower towards the surface of the earth. And as I just said, as you're at the top, you've already started to rain. So now you have very little water vapor in you, and your air will begin to sink and it'll start to warm up. So on one side of our mountain, we're going to see, very large rains and all that. And on the leeward side, it's going to be what we call the rain shadow. You're going to see next to no rains. And you can kind of see that on our mountains. If you look at California, when it's not burning, when you can see that right before the mountains, that's where you have a lot of the rains. And then you go to the opposite side of the mountains. Like Kansas, I'm not saying Kansas is a desert, but you can see that there's a lot less rains when you get there. Look at Nevada, definitely very little rains. All right, so that's what we call adiabatic heating and cooling. As you go up, less pressure, so it expands and the rain droplets cool, so it falls down as rain. As you lower, the pressure pushes you closer and closer together, causing more heat, and you'll get warmer air. Okay, again, that's that. Low pressure goes up, we have lots of rain. High pressure goes down, rather clear skies. Latent heat release as well. Rising air, again, loses that heat energy, and cooling air is going to gain some of that heat energy because of the pressure. And again, we're going to call some of these things these convection currents. Now, I had a beautiful little setup, but it takes a long time to do, so I couldn't actually do it for the video. But basically, is two large tubes that are connected laterally. And if you put hot water in one and cold water in the other, you can see that they start to swirl. And that's what we're going to call a convection current. If you happen to have a convection oven, basically, it heats up from the bottom and the air starts to rotate around. So as it goes up, it starts to cool off. It'll begin to sink and warm up and continue again. Apparently, there's something scary at my house and my dogs have to alert me. All right, so convection currents are super important because that helps to describe a Hadley cell. So on here, we're going to look at a map here in a moment. Okay, you definitely have to know about Hadley cells. There's another one. If you just know about Hadley cells, that's perfectly fine from there. Okay, they're the same thing. I apologize for my dogs. They all need to be quiet. Anyway, so Hadley cells. This is that. What's in the middle? So that little shape in the middle, that happens to be a cloud. Okay. So that low pressure we talked about raises up. We're going to lift up the air. And as it does that, we expand. It's going to rain. And that's what gives us our clouds. Now, as it raises up, it's going to push the air off to the sides. So that's where that 2A and 2B, the air is going up. It pushes the air that's up there off to the sides because we have that expansion. So now we're going off to the sides. It starts to cool. And so again, cold air lowers, it falls down. So that's when we see on our sides right there, the threes, they'll fall down. And when they hit that, we're getting air pushing down. So that's our high pressure. We've already lost all of our rain. So you're going to see at the 30 north and 30 south on our latitudes, you're going to see rather dry areas. And at 0 degrees, our equator, that's where the majority of our rainy areas are going to be. So we're going to drop down. It's going to be very warm. And because the uplifting air, there's a vacuum. So we are going to pull the air from the sides. And that's when it starts to circle like this. So we have the air rotations going up in the middle, out to either side, fall down, and rush back towards the middle where they can pick up more water, get heated up by the sun, bounce up, rain, fall back down. And again, so we have these nice little concentric circles going around. That's what we call our Hadley cells. So I have a map I'm going to show you. Hopefully you're going to see this a little bit easier. You see right there in the middle of the map, that's our equator. On either side of the equator are our tropics and all. So you're going to see a lot of the air being uplifted there. We call this that uplifting. And you can see right at that equator, if you look on that tiny little map, you'll see a lot of green areas. And it's because there's a lot of water that's dropping. You'll get lots of rain down here. Okay. Then, as it goes off to the sides, going towards 30 north and 30 south, the air is very dry, falls back down, and it starts to create high pressure. So we're going to see lots of higher temperatures. And look, 30 north, that's the top of Africa right there. That's the Saharan Desert. Parts of the Middle East. Now, if you go up to the next ones, you look at 60 north, 60 south, we've got more uplifting air again. So again, the air is going to lift up. It's not necessarily going to be rain this time. It can be snow, it could be rain, it could be sleet, but we're going to have that uplifting air and it bounces out. Now, one of them is going to go towards the pole. The other one's going to go back down to that 30 north and that 30 south. So again, more dry, warm weather relatively. And we'll make those Hadley cells happen again. So this is another form of where the air is going, up and down and around. So we haven't talked about all the other little lines on there, which direction they're going, north or south or east or west. That's in our next one. So before I do that, I need to switch my screens because if you see the little button down the bottom right, it's earth.nullschool.net. I'm really hoping you guys have seen this before because if not, I hope you've never seen it before is what I should have said because it is absolutely awesome. So let me swap my screens here real quick. You can see my awesome wizard-like beard. I'm going to close my little video and give me 1 second. I have to swap my tabs. I absolutely love this website. So I'll put a link here Control C, into the chat so that you can see it too. If you want to click on this link right here, copy that. Oh, so this right here, this is actually showing almost live. It was, in this case, let's see, it was recorded earlier today, about 50 minutes ago. These are the actual weather patterns. These are the wind patterns that we're experiencing on the earth right now. Okay, so we're going to talk about how we get those patterns, but I'm going to zoom in. Are you guys able to see this on your screen? It probably lag a little bit before you get to it. Can you see? Oh, it is. Like I said, this right here, this blows my mind. This is absolutely wonderful. When we were having hurricanes, I could actually track where the hurricanes were going. You can see where the winds are traveling, and again, like I said, I'm in North Texas. I was getting some lovely little cool air. Look way out off to the side over here. Let's see. I'll zoom in. Come over here. Look, we got some nice big rotations happening. By the looks of it, Alaska is going to get some nasty little weather right there. If I had the weather up, I'd actually see what was happening. So I love this website because there's a lot more to it. It's not just these winds. You can change them also to, let's see, that's wind surface. Let me show you. Ocean patterns. Not nearly as impressive, I know. But you can see like basically which direction the water is flowing. You can have waves. Here is the currents themselves. You can probably see some of these maps on TV. I love this website. Now the brighter colors are obviously going to be your warmer temperature. So you can see right there on that equator, that's where that warm air is. That's where that air is going to lift up and start having that convection current occur. Like I said, this right here. Oh, I love this website. Probably one of my favorites. I know I'm running out of time. I'm using too much of my time just to play with this website. So please, look at it. There's a lot of information that you can use from this website. It's amazing. All right, I gotta go back to my PowerPoint screen here. My Google slide, not PowerPoint, my Google slide. Let's see, make sure that's the right one. Yay! Okay, here we go. So, So, look at these funny little, curvy lines on here. I'm actually going to demonstrate this here in a few minutes. Now, I was afraid that I would not have enough time to discuss the Coriolis effect effectively. So I put these two links in there, and I'll put them into the chat real quick for you. This first link is actually who I was using to help understand the Coriolis effect myself when I first started teaching this. This guy is an actual physicist and scientist, and he uses drones to actually show you from different perspectives the Coriolis effect. So before I continue, let me actually tell you what the Coriolis effect is. It's the Earth's winds are technically forming in a straight line, but because the Earth is rotating, we mentioned that earlier, that's the Earth's rotation is what's causing some of these patterns. It's trying to go in a straight line, but because the twisting of the Earth, it's actually curving. So if you look on that map, you can see that at the equator, the winds are going down towards it, but they're curving off to the left. So in the northern hemisphere, we'll see that there is a clockwise rotation. In the southern hemisphere, though, it's a counterclockwise rotation. And that, of course, brings me to one of the more famous questions. Do toilets go the opposite direction in the southern hemisphere? Do y'all know the answer to that? Do they actually rotate in the opposite direction in the southern hemisphere? Because lots of people have been trying to figure it out, and people have been trying to prove it or disprove it. So that second link right there, and I'll copy and paste that. Two guys, they run each one of them runs a different video vlog. They got together, and over the course of time, they attempted to prove that, yes, it actually does. Spoiler alert, it does rotate just like the winds do in the southern hemisphere. They're going to go counterclockwise. Northern hemisphere, they're going to go clockwise. And if you go to that web link, don't do it right now. I'm not done talking yet. They actually synced up the video. That's one of the very first times that this has ever been done. So they both have their video going one above the other. And as one talks, the other one's doing something. It perfectly syncs up so you can see it. It's a really neat little system. So, like I said, brought my prop my little globe here, my little writable globe. So hopefully we can see this happening today. Where's my little black marker? So here's my globe. You can see the equator and all that. Okay, love little land masses. You don't actually have to worry about the land masses right now. But, oh, there we go. Sorry about that. Okay, so if I'm at the North Pole and I want to go south, I'm going to draw a straight line. Without the Earth rotating, it goes perfectly south. Not a problem. No deviation, okay? What happens when I start spinning the globe, though? Okay. And which way does the globe spin? Am I spinning it correctly or not? So let me try it again. So right here, I'm going to basically just move my hand down, but I'm going to attempt to spin the globe at the same time. Okay. So ready? 1, 2, 3. That was terrible. But you can see, look at that. It started to rotate clockwise right down to the equator. Even though I only moved my hand straight down, relatively, kind of, it started to rotate. And we can see that this rotation is happening. And it's going to happen at most, at the equator, the 30, the 60, and all that. What if I did it from the southern hemisphere? Would I have the same results? Is anybody there? Did I lose everybody? Hello? Okay, good. Is everyone got quiet there? Okay. So if I do it from the southern hemisphere, again, if I rotate I try to go straight. It's very difficult to do this with two hands and be able to backwards. You can see that it's rotating backwards up here. It's going towards the equator, but in a counterclockwise fashion. Let me erase this real quick. Use my handy hand. Let me start at the equator. All right, so quick question. I'm going to start the equator, and I'm going to go up, and I'm going to rotate my Earth. Which direction will my line go? Will the line go to my left, which is your right, or will it go to the opposite right? My right versus your left. Will it go to the left of the screen, or will it go to the right of the screen? You're right. It's never going to be straight. It's trying to go straight, but the line itself is not going to be straight because of the Earth. All right, so let's find out. So again, I'm going to rotate the planet accordingly. Wait, hold on. Yeah. So I go up. I tried, right? There we go. See, look at that. It's starting to curve, and it'll go up like that. So we're going up. As we're going down, and we're going up. So again, we have that clockwise motion. Now it just made a big mess, or it looks like some sort of football tactics are happening here. Okay, so I will tell you right now, I do not explain it nearly as well as either one of the gentlemen. Now, the physics guy, I liked him because he showed it with drones from lots of different angles so that you can experience it if you're standing on the Earth or if you're above the Earth. It was really cool little video that helps really understand the Coriolis effect. Now, the other two guys, they explain it a little bit, but they help to show, the difference between northern and southern hemisphere really well with the circling of the water down the drain. And they kind of talk about some of the fallacies that people have come up with, like you can't actually trust your toilet. It's because there's like sometimes your toilet has actually like little flanges in there to actually push in one direction or the other. So can't actually trust the toilet. So they came up with a system to prove it pretty well. It convinced me, so I was very happy about that. So I'm hoping beyond a shadow of a doubt that I was able to help you understand a little bit tonight about Earth's atmosphere, the components of it, and how those components and other factors help to give our global wind patterns. If I've done my job tonight, I'm hoping you'll give me a thumbs up or a yes. If I haven't, please tell me. I'll try my best. I can stay here for a little bit longer. Thumbs up, awesome. Again, hit those other little YouTube videos and websites, especially that global wind pattern. I can just stare at it for about hours. It's great. Are there emojis? Actually, yeah, I think there are. Hold on. In my little chat window, I got emojis. Look, I'm very innocent when it comes to knowing things. A little smiley face on the side there in the chat window. Let me think about anything else that I can come up with. I'm sorry. I didn't do as many dad jokes as I usually do. I apologize. I will get on my game. I've been up since 3 a.m. I'm very tired, and I have to go to GameStop to go buy a Pokemon game tonight for my son, so I'm going to be very tired. It's the other reason why I'm going to take the day off tomorrow. All right. So, last but not least, I cannot let you leave without reminding you once again that we are at Think Fiveable. We're on the Twitter. We're on the Instagram. Of course, we're on the YouTubes. And of course, we're in the app, too. Hopefully, you guys are a little bit more educated tonight, and I hope I've done my job. Yeah, we're on YouTube. Look it up. We're on, look up Fiveable or Think Fiveable. Okay. Not all of our videos are out there. Some of our older videos are going to be out there. Okay. But I know tonight's video will be in on our website. I'll get it up there tomorrow, and I'll make all those links in there. And of course, if you ever need us, we're there. We're here to help you. And of course, your teachers are there too. So, as far as I know, there's not a study guide for apes yet on Fiveable. I know it's in the works. It is one of the things that we talked about and planned. I know some of the other subjects have it. So we are attempting to get one. But because of the new curriculum that we're going through, a few things had to get changed from some of the previous ones that I used to use with my students. So I will, if I can find one specifically for the wind patterns, I'll put that in the comments section with this video tomorrow when I upload it to our website. So is there anything else I can help you all out with before I call it a night? All righty. I see no type-ins on the chats. So I'm hoping that everybody got a little bit of something tonight. I hope you found something special. And of course, not a problem, Carla, and everybody else. I'm here for you. So are the rest of our friends here at Fiveable. Have a great night, and I hope to see you again at some of my streams or some of the other streamers. So have a good night. I'm going to have some dinner and a lot of coffee. Take care, y'all.